recording is going. So I'm going to copy the folder from the other day. Duplicate. Give it today's date. And go in here and I'll get rid of one sample because we're done with that. I'll open up the two samples project. Files, and I'll open up the two sample script we had. So we had this data that we'd read in. It was two groups, Nova Scotians and British Columbians, and IQs for those two groups. And we can get a sense as to how these two groups were distributed in their IQ scores. And this, I guess, is just some code to show you. I was showing you the shape of various curves that are available to represent your beliefs. And we had this tosample01.stan as a file where we had the data coming in just from each group separately. And our model was such that there was a mean for one group, mean for the other group, standard deviation for one group, standard deviation for the other group. We expressed some priors for each of those things, but then otherwise just expressed each group as a normal distribution with its mean and its standard deviation. Which meant that we had to do some work after the fact to address the question, are these two means different from one another? What should we believe about the difference between these two means? So we had that if we sort of ran this and created this object called post, we would have to extract out the samples for each mean, and then we would plot them, and then also we can do a difference score between the two means. And we get the histogram of differences and the credible interval for the differences. I showed you that you could actually do the same thing for the standard deviation, so you could speak to not only differences between the groups in terms of their location on the x-axis, but also the amount of variability there is within each population. Oh, question?
So just to review, can you go back to the STAN file briefly?
Yeah.
So in this one that we did, our priors were informed by the data, right?
Yeah.
Which are reflected like in the parameters as well as in that y1 mean, y2 mean?
Well, actually, we actually didn't use any of my tricks. We actually used just our prior knowledge about IQ scores.
Okay, because I saw that there and I was trying to remember if they were informed by the data or they were not. So
yeah, so here they're not really, I haven't shown you any tricks for this
so those are not,
part yet.
What's in the parameters section right now?
This is each individual mean and each individual standard deviation. Each group's standard deviation, each group's mean. So, yeah, another question?
I wanted to, I also wanted to make sure I thought this last time, but I want to be sure. The advantage of using the Weibull distribution is that basically compared to the normal, it gives us a zero credibility of having a value of 0.
Yeah,
okay,
yeah, exactly. So if I go up here to this curve thing.
It starts at 0, 0 instead of starting like,
so it starts at 0, 0 and comes up. If we'd had a D norm and a mean of 15 and a SD of 20 maybe. Do something, but it starts really high there. And we literally don't believe a 0.
So it suggests
Weibull is nice.
Consider 0 to be.
You could also, if I do, this is log normal, mean. You know what, I'm not going to do it because I can't remember the proper shape for it. We might come back to using, instead of a Weibull, a log normal, but might do that at the end of class today.
That would also start at 0, 0?
Yeah.
Okay.
Yeah. So, yeah, last class we had this model We actually could have run the very first model that we had, where we had the mean of just a single group, and we could have done a model for one group and then rerun that same model in the second group in order to get this different score thing. So we happened to choose to put it all together in one single stand file. But it's a little cumbersome to have the model expressed like this, but then to actually be inferentially interested in something different, that is the difference between these two values. So what could we do instead?
Have two models?
Could have two models. We'd still need to like combine them. So one model for one group, one model for the other group. We'd still have to combine them afterwards to talk about the difference between groups.
So what if you, so are you, sorry, maybe Dylan, you want to say something?
No. You.
So you're saying here like it's cumbersome because all this like, it's all jammed together here, right?
No, it's actually not that it's all jammed together. It's that it's the way we've chosen to represent this scenario. Maybe it's easier to, I'll show it in paper. If we imagine a plot like this, where we've got I, Q on this axis and group on this axis, and N, S, and B, C, there's a whole bunch of dots for one group and a whole bunch of dots for another group, and we've chosen to parameterize it such that there's some mean and some variability, and for this group there's some mean and some variability. And then we had to go in and afterwards say, okay, is there a difference between those two means?
So what if you just built a model that is, instead of trying to get the mean and standard deviation of each separate one, just ask for a model showing the difference between these two groups and have that be the thing
Right.
you want to estimate?
Yes. So in the model itself, we want to express that there's two groups, there's a difference between the two groups, so we can express a belief about values for that difference. So that's this little bit. What other thing would we have to have in the model? If we've got a model with a difference score between the two groups, I'll give you a hint. You always need two numbers to describe two groups. So if you have the mean of this group and the mean of this other group, that's two numbers. If you have a difference score and some other number, that's again two numbers. What is that other number that we would need?
Instinct says something to do with standard deviation, but I don't know.
No, we're not talking about the sort of variability within the groups yet. We're just talking about, imagine you just have literally 2 points, 1 point here and 1 point there. You can describe those points using the position on the y-axis of this point and the position on the y-axis of this point, or you could describe it in terms of the difference in the position on the y-axis of these 2 points plus some other number.
No difference?
That's actually correct. Yeah, the average of those 2 points. So what is the center point between these two? So you imagine there's some sort of point in the center. And the question is, what is that sort of point in the center? So another word for that point in the center is called the intercept. So you can think of this model as if you actually had this as a number line and you artificially put 0 right in the middle, then this actually becomes, if you try to connect these two means by, I didn't actually make it very slopey, but by a line, the point where it crosses the line is the midpoint between the two groups, and it's also the midpoint on the y-axis between the two groups. So the point in terms of high school geometry, the point where the line crosses the y equals 0 is the intercept. So we want to take our model. I'm actually going to create a copy. 2, 2 samples, O2. Open that one up. I can close the O1. And now, instead of Y1 mean and Y2 mean, we want intercept and diff. I have a question over here.
Just trying to like visualize. So, I mean, the intercept, or rather the difference, would give you a whole bunch of samples in the posterior.
Yeah, we'll get samples in the posterior for believable
Yeah.
values for what the difference between the two groups is.
Okay, and then similarly, we'll get believable values for what the intercept between the two
Yeah.
means. Okay.
Yeah, so we're not typically that interested in that intercept term. It just reflects where on average the groups are on the number line. So, but we are interested in the diff part. Now we've got some choices to make here with regards to these other two parameters, y1 SD and y2 SD. If we wanted to, for now, I'm actually going to reimpose that assumption of homogeneity of variance just because it's a little less typing at first. We can ease off on that in a little bit. So I'm just going to call it YSD. So we're imposing the homogeneity of variance. So wherever I see Y2SD, I'm going to get rid of it. And YSD. All right, so we still need to say the intercept. Well, actually, yeah, intercept there. We'll say this is diff. I'm going to take off these because we'll have to generate ideas for new ones there. And take those out. Okay, so what do I need to have here to express this model as we expressed here? Because we still need to say this mean is some function of these two things, and this mean is some function of these two things. So what do I need to put here?
The mean and the standard deviation for your normal distribution.
Yeah, so we've got standard deviation there.
Right.
So I need to decide how to combine these two things to get to this mean, or to get to this group's mean. And I'll switch over to my camera to make it maybe, you know what, I'm going to make a more dramatic example here. Just going to put 2 dots, call this Y1 and Y2. So there's 2 dots, and I can describe them in terms of Y1 and Y2. But instead, we're going to describe them in terms of a difference and some sort of halfway point also
So
between them.
one is intercept minus diff, and the other is intercept plus diff.
You have to.
Yes. Yep.
Good.
Yeah. Well, that's it. Minus diff divided by 2. And this one is plus diff. And if I happen to call one, so this one kind of conceptually, if y1 is less than y2, diff is going to be forced to be positive. But if I had that backwards and y2 is actually less than y1, that'll just flip the sign of what diff is. It'll make diff negative. So it doesn't actually matter which one you make positive or negative. That just influences the sign of what diff is. So for the intercept, what sort of belief do you want to represent? Prior belief, prior to seeing any data. Oh, yeah, go ahead.
Can I just ask a question? So y1 is no longer about the mean of y.
Y1 is now, so this represents how to get the mean of y1.
Okay, so it is about the mean of y. Okay.
Yeah.
And so you
Yeah.
just work backwards from the generative model to get to that.
Yeah.
So it's defined now instead of in terms of our expectations with the mean.
Yeah.
Our expectations with the difference between.
Yeah.
Okay.
Yep. So what belief do we want to represent prior to seeing any data about the overall average IQ regardless of what group you're in?
Probably also 100 as the
probably normal.
Yeah, norm. Sorry.
100, maybe make it pretty wide, 30. So kind of what we had for, not kind of, exactly what we had for each individual group all by themselves. What about this difference between the groups? I'll give you a hint. Probably makes sense to have a normal distribution. What would we, not seeing any data, what would be sort of maybe the best peak point for our belief distribution? 0. Yeah. So to be nice and skeptical, we can reflect no belief in either a positive or negative difference, or no bias in belief towards a positive or negative. But we still want to make that nice and broad, so I don't know, 30 again. So that's probably ridiculously broad, but it's still sort of an order of magnitude related to the amount of noise that we're expecting, about 15. All right, so I'm going to save. Actually, I'm going to click that check on save. I'll click save, and it tells me it is syntactically correct. So I'm going to go back to my 2 samples bit, and I guess, nope, I have to go all the way up to here. So I'll copy this little bit, and I'll go to the bottom, and I'll paste. So now instead of, I'll call it post 2, instead of 2 sample 01, it's 2 sample 02. I should be able to hit that. It's going to compile first, and then it'll start sampling. So I want to print out the summary table from post 2. Once it compiles, it should sample very quickly.
Is it faster to do it that way than do the 2 separate and then subtract after?
No. Well, I don't know. I haven't checked.
You didn't change it.
There we go. What were you saying?
You didn't put like any kind of difference indicators in the R file. That's only in the scan file.
Yeah. So I pointed it to the stan file that has the model that implements this intercept and difference parameterization. You'll hear me say parameterization a lot. That's what I mean, is that you've switched from talking about 2 means to talking about an intercept and a difference. So this is sampled. Get some warnings, but the counts are fairly low, so we can ignore them. We'll make this bigger, print it out, and you can see that instead of now a mean for each group, and we then would have to do some work to do inference on the difference, we actually get the overall mean of the 2 groups, the center point between the 2 groups, and the difference. So we actually get out the table, or the values that we want right away. Now it should be generally the same, except for the fact that I impose this homogeneity of variance assumption. That probably will, no, I can't recall if that's going to influence things or not. Certainly this credible interval for the difference between the 2 groups excludes 0, which is as expected because I generated the data with a non-zero difference between the groups. We could do a visualization of that distribution, but for something this simple, it's pretty easy to tell that it's beyond 0, and it's roughly symmetrical, about 4 points on the other side. If we are interested in this intercept, like where are the 2 groups overall, we could look at that. And indeed, we can combine these 2 to figure out what each group's individual mean were, just in the same way that we could combine the 2 groups' individual means to get out what the difference score is. We can combine the intercept and difference to get out what the individual groups' means are.
Is there some like succinct way to just put that in code so it gives you everything? Because when you kind of want to report both
Yeah.
groups' means.
I'll show you I'll actually give you guys some code to do that, to combine that easily automatically.
I guess, yeah, it's just.
Yeah, we could have done it up here in code by grabbing up the samples and then adding them for one group and adding the diff to the intercept for one group and subtracting the diff from the intercept for the other group. But this is, for now, yeah, I don't want to bother doing that now, or I didn't actually prepare that yet. Question?
So, so our last time at the end, what we did is we showed up when you subtract all the values of one group from all the values of another group, what that curve looks like.
Yep.
And then we did the 95% credibility.
Yep.
And from that is that basically I'm asking, is that roughly equivalent
Yeah.
in terms of like, if that were to overlap with 0, you'd say, okay, maybe there is no difference.
Yeah.
But okay.
Yeah.
Thank you.
Yeah. Okay. So we're generally going to use the intercept and difference parameterization for most of what we do, not the individual means, just because we can get out the thing that we're interested in most right away, and we can express our prior on this thing very explicitly. It was implicit before when we had this model, and when we said we had a prior on both of these, but it's the same prior. That implies a prior on the difference, peaked at 0, but tapering off with some unknown amount of sort of standard deviation there. Here we can, with the intercept and difference, we can be really explicit about that.
But if they weren't, if it wasn't, or if they didn't have the same prior, you could, maybe say that the diff was maybe 4 or something.
Yes, so if you wanted them to have, if you, for example, had an actual prior of 110 and 100, then you'd want to reflect that one here,
Okay,
a
cool.
difference of 10. Usually, you want to use a prior on the difference of 0 difference and let your data convince your reader that there actually was a difference.
Yeah, if you're comparing two groups of the same type,
Yeah.
under different conditions, yeah, you would want it.
Yeah.
That makes sense.
All right, so we're close to doing this as regression. So to do this as a regression model, so right now this model takes in the data as two separate things, two chunks, and then says, okay, this chunk is distributed like this, and this other chunk is distributed like this. It would be nice if we could actually make it so that instead of having it like encode as two separate chunks, if we could just be able to pass it in some indicator variable that says whether it's group 1 or group 2, and have the generative model here expressed in terms of, okay, go up the diff if the indicator variable is, say, 1, and go down the diff if the indicator variable is, say, -1. So I'll do that, and I'll pause as we do it to more explain what I mean by all that. So I'm going to copy this model, copy, call it number 3, 2 samples, number 3. Open that up. So now instead of n1, y1, we're just going to have n, because we're going to have a total number of samples. And we're just going to pass all the samples in as one long thing. But in addition to a vector called y, we're going to have a vector called x. So So the y's contain all the IQ values, the x contain some sort of indicator as to what group the people belong in. We're still going to have intercept, diff, and the amount of noise. But we're going to change this so that, again, we don't have y1 and y2 anymore. We just have something called y. So what I want to change here is add in that this intercept, well, I'll put it as plus x times diff. So that will make so that I have to create this x so that whenever x is -1, it's one group, or whenever x is one group, it's -1, and when it's the other group, it's +1.
It's just for like binaries at this point.
Sorry?
It's just for
Yeah,
binary
so
groups.
x is now a categorical indicator variable.
We had like a third province or something. You have to work out different math.
Yes, yeah, exactly. We'll get into that shortly. All right, so I'm going to go back to my toSamples.r and scroll up till I can grab this. Oops. So I'll create something called post3. toSamples3. So again, I want to pass it in something that is called n, and it just has to be the number of rows in A. And pass it in something called y, which is just the IQ. And it wants something called x, which is the group labels turned to -1 for one group and +1 for the other group. So there's a couple ways I can do this. Let's see, what would be the best way to do this? I'm going to show you, let's see. Yeah. Okay, so there's a few ways to do this. The way that I'm going to show you right now is a little bit more typing than other ways, but it will introduce a tool that will be useful to you guys. So I can just put it down here, I guess. Model.matrix. I'm going to call the function model matrix, and whatever this function returns will be assigned to x. So what that's going to be is this model matrix function is a function that, well, I guess the only named thing here is called object. You can take a look at the help. It's not super useful without examples, so it's best described by example. This object needs to be a formula. So it starts with a tilde, and you express it as the names of columns within the data set that you want to refer to. So I actually can't remember. Let's view A. Yes, there is a column called group. And I lie. I'm going to actually create this outside here. I'll call it mm. What's that? I also need to give it a data argument so it knows like what data set this is coming from. So if I create this thing called mm, and I'll just take a look at it. Ah, this actually is going to have the intercept in it already. All right, I'll build up to this. So for now, I'm not going to do this. Instead, I'm going to take the A group, the group column within the dataset A. It's already, I think, str of A. oh, not question mark str, just STRA. Group is just a character vector. A quick trick to oh no, I lie. I'm gonna maintain that model matrix. Control Z. It's given me this model matrix where it's given me two columns, an intercept column that's just all ones, and another column that's ones and zeros.
You specified $group, so why is it also giving you
An intercept as well, because whenever R encounters a formula like this, it automatically adds in an intercept, unless you turn it off by putting a 0 plus. We will typically actually want the intercept, in which case, here, let me actually just say,
Wait, but that the thing just now came from the model matrix, or did it come from x equals a $group? The the double column. I thought that came from when we looked at when you just had
okay, so I'm gonna keep it as just that, run, and I'll just say mm. And so mm is created by a call to model matrix. It's seeing that we want to create a model that has group as an effect. It has automatically added in an intercept for that. Question?
Is the intercept for that, what does that represent?
It has just added, it's tried to be helpful, and it's trying to add in just something that we actually will use in a moment.
Okay.
I just want to build up to it first.
Okay, sorry. Then.
Yeah. So this actually hasn't given me what I wanted. It's giving me an effective group, but instead of ones and negative ones, it's giving me 1 and 0. So for every entry that it had NS, it's giving me a 1, and for every entry that had a BC, it put a 0. I don't want that. I want ones and negative ones, right? So the way to fix that, do I have to do it in model matrix? Contrasts. Let me try. A list whose entry values, numeric or character strings, naming functions to be used as replacement for contrast function. Oh, okay. Yeah, that's going to be a lot of typing. So the way to make model, you can tweak model matrix using the contrast arg thing, but that's going to be more typing than I want. There's a way to set the way it defines contrasts. And that's what we're really doing here, is we're asking for the contrast values from a model using group as a predictor. But there's different ways to compute contrast. You can have what are called treatment contrasts, which is what this 0 and 1 is. There's another type of contrast called sum contrast, where they sum to 0. So one is -1, the other is +1. So that's the one that we want. So to make it so that model matrix gives you one or the other, it by default gives you treatment contrasts. What you want instead is to give you some contrasts, invalid value. Oh, because it wants. I think. Okay, so this command where you say options, and I'll put it on different lines here, and you say for the contrasts value of the options argument, contrast argument of the options function, you pass it this list of 2 strings. What you put here defines what it does with categorical variables like group is here, and S and BC. What you put here is what it does when you ask for like things that are polynomial contrasts. So if we won't ever use them. It requires you to put that there, though. You can't just tell it to put just contrast sum. So,
So sum is for if it's just 2, and poly is for if it's more than that, or?
it's not, no. Contrast poly is for numeric variables, and specifically how it handles when you've got polynomial, like you want to do
I guess I
a
would
square and the cube and the etc.
Okay.
I don't actually ever use that.
I guess I would have to see an example. So yeah, don't worry about it.
Maybe you don't want to do it this way for experimental purposes, but I'm surprised there's not a way to just like rewrite the data where every time it says NS you see -1, and every time you see
Yeah,
+1.
we
Like,
can do that.
Yeah.
I wanted to introduce this model matrix thing for the purposes of when we start getting into regression models with many values. It then becomes faster than doing this recoding.
Could just do that.
And doing interactions and things like that. This computes the contrast for an interaction automatically rather than us having to do it by hand. So yeah, for this particular example, it probably would have been faster if we just used one of the tools that I've shown you already to replace all the values that are NS with -1 and the values that are S or BC with +1. But I wanted to introduce this as early as possible, and I'd forgotten that the default. See, most of my scripts I have this at the very top anyway myself. So, and just FYI, this options function changes something about the global behavior of R. It doesn't return anything. It just changes R's global behavior. So you don't expect it to have any printout or anything. But having run that little bit of code, I can now run this, and MM should now be 1s in this second column, 1s and -1s. So if I know MM has 2 columns, one of them is intercept that I don't need. The other one is a column of the contrast that I want for that group variable. I can then come down here and say MM. I might be able to refer to it by name, actually. It's called group 1, isn't it? MM group 1. So let me, no, I think I have to say just the second column. So I think this will work. So I want the second column in this matrix that is returned by model matrix.
You can figure it out from the column heading.
No, I guess there's name. So matrices are weird things because they have names, but sometimes you can refer to them by name, but sometimes not. I guess this is a case where you couldn't refer to that column by name. All right, so it ran again. If we say, I guess I'll copy this little bit up here. Print post 3. We should get the same numbers as before. It's now +4 instead of -4, and that's just because which one got labeled as -1 and which one got labeled as -2. It flipped between what we had, or -1 and -2. It's -1 and +1. They got flipped between the two ways we were doing it. The final thing.
Actually, never mind.
No? Okay.
Figured it out.
Well, I guess. So let me go back to the stand code for this scenario. So what would we do if we wanted to, if we didn't actually have that intuition that IQ scores are around 100 and have about a expected variability of about 15? What would we do to sort of impose some default priors here?
Generate them from the data again somehow.
Okay. So the tip I'd given you, so we have to do something to the data. So this AIQ. So what had I suggest did you do? What is one technique to do to the data?
We will make them into standard scores.
Sorry?
Make them into Z scores?
Yeah. So we can do that using the scale command. And remember I told you had to put this funny square bracket comma 1 after scale. So that's going to take whatever's in the IQ column, subtract the overall mean, and then divide by the overall SD in that column. So that's the subtracting the mean it's not each group individually, it's just all the data regardless of group.
Oh, okay, so across both the NS and BC
Yeah.
groups. Okay.
Exactly. So having scaled the data, what would good priors now be? Where should our peak for the intercept be? Peak belief for the intercept.
0.
Okay, why is that?
Why 0?
Yeah.
Because that's the mean of the Z scores.
Yep, exactly. So by translating the data into Z-scores, we've actually imposed that this thing intercept has a mean of precisely 0 in the sample. We probably want value not of 30, but maybe 1. What does that 1 reflect?
1 standard deviation.
Yeah, so 1 sort of
That's just
unit
why
of noise as observed in the data.
That's why I was laughing, just imagining like if we considered it credible to be 30.
Yeah, 30 standard deviations away. Yeah.
But like previously, we had more wiggle room because our standard deviation was at 30, which is double what we kind of expected in the data.
Yep, so if you want to make that 2, that's fine. Probably going as far as 10 would probably be a little too much. That's as far as I would go, maybe. But it shouldn't, if you have enough data, usually normal 0, 1 is fairly weakly informed. If I only had like 10 data points, maybe I'd want to make my prior less informative. But here we have like 100 observations per group, so the data really is going to dominate. So this actually, so what should we have for now also our prior on the difference? Where should it be peaked now that we've scaled the data? Yep, still at 0. So despite the fact that we've shifted all the data down so that all the data is down to 0, we still, the way the model is being parameterized, we still are talking about a difference between the two groups, so we still want that difference as being peaked at 0. But we probably want to drop this back down to about the same sort of standard deviation as we have on our uncertainty about the intercept here. Just again, because that's kind of reflecting in the units of the Z scale. Our Weibull distribution, having a 2 and 20 made it so that it was peaked around 15. We could go back up to our curve code and figure out a better one, but I'd actually shown you before that 2 and 1 here creates a curve that is peaked at about 0.8, 0.9. And that's a pretty reasonable curve for this default when you've Z-scored the data.
Can you remind again? So 2 is the shape of the Weibull.
Yep.
And 1 is what?
Yeah. 1 is the scale, so how broad it is, where that peak actually is. All right, so this actually, it didn't make a ton of sense to have these default values when we were doing the 1 sample Z. Here, it makes our life a whole lot easier in that, remember, we were a little bit concerned about having a prior on the mean for the groups that's centered on, that has its peak value at the sample mean, because that's the thing we want to do inference on. And so it was weird to scale the data so that we were expressing our prior to be peaked at where the data's sample mean actually was. Here, it's a lot clearer, the utility of that scaling, in that we've scaled it so that now we have one of the parameters peaked at the value that we actually observe in the data set. But this parameter we don't care too much about in the first place. We don't actually care too much about like what the intercept of the two groups is. It's this other parameter that we're actually interested in, and we've intentionally set that to have that peak at 0. But scaling allows us to have, first of all, not think too much about what we have to have here, but also then have this expressed. Really, what this is actually doing is it's now expressing the our prior on the difference on sort of Z scores. So we have our difference prior tailing off on either side, so that I guess 64% of the credible values going into it lie between -1 and +1. If you are somewhat familiar with psych, that actually is even generous for what you'd expect for effect sizes in psychology. Usually it's around 0.3, most of the values are. So this allows us to convey a prior a lot more easily.
We haven't changed much mathematically. It's just made it easier to kind of represent.
No, exactly. Yep. So we haven't really changed anything mathematically.
I mean, it's still based on like the data in the sense that we scaled the data, so it would be peaking at 0.
Yeah, the intercept is now peaked at 0. But yeah. So if I save, check on save. Yeah, syntactically correct. Go way down to the bottom and sample post 3.
Well, that's running. Previously, X was equals IQ $group.
Yeah. Or sorry, previously we didn't, or actually we just, yeah. Nothing's changed actually about X. We remember, I guess, we just modified now what the priors were.
I thought X is our contrast, like our indicator.
Yeah. So X hasn't changed. It's still -1 and +1. It's that that column from the model matrix.
Yeah.
And what's changed is that we, in terms of the input, is that we scaled Y.
But I mean, previously it's in the 2 samples _ 02.
Ah. That was before. Yeah. That was when we actually had the data coming in as being segregated into 2 groups. Yeah. Now, in this posterior, when we print it, I'll make it bigger so it fits all in one thing. We now have the intercept. Don't really care much about it, but it's peaked at 0 as expected. And the difference, this again is on the Z scale. So if we wanted to convert back, we'd need to multiply by the standard deviation of the data coming in, which you typically really do want to do. But I'm going to show you guys how to actually do the scaling and unscaling actually in your code itself, so you don't have to do this every time. Before I do that, any questions about this bit?
A little bit. It might be back a step or two.
Sure. No.
So could you go to the stand file?
For 03?
Yes.
Mm-hmm.
Okay, so so for the intercept, sorry, I'm just trying to think. So we set a prior to for the intercept of 0, which is, I mean, for when we standardize the IQ data that's the equivalent of 100.
Mhm.
But if you were to actually take the means of those standardized data set, it would be like the intercept from the data set would be like, what would it be, like 0.1 or something like that? Does that make sense? Because the mean of those IQs was altogether a little over 100.
Yes,
right?
yeah.
Okay.
Yeah. So
that's what I was
we
saying.
actually, yeah. So this prior centered on 0 given scaled data actually reflects a prior centered on like 10. Let me go up. Is about 107. A prior centered on 107 in the unscaled data.
Okay.
So yeah, we've changed from, if we were thinking about this as a scenario where we did have good information about what that intercept should be, then we wouldn't want to do this scaling stuff. But if we were not psychologists, didn't know that it should be about 100 and wanted to just have some nice default prior to put in, that would make it so that we're using a slightly different prior than we would if we actually knew what was the expected mean there.
Right.
But given the amount of variability that we're adding into our priors, it's not a big difference.
It's not even,
Yeah.
Okay. So I just want to make sure though that we've set it up so that prior intercept is now in effect just something generated from that data set.
Yeah.
rather than-
Yeah.
Okay.
Yeah.
And then the diff is also generated from it, but it always was because it's this minus this.
Yeah.
So okay.
You said at the beginning when we started this like 03 version that it was going to be kind of a predictive model. It seems to still be just comparing two groups, one labeled like negative and one labeled positive.
Yeah. Yeah. No, I called it regression. And that's all that regression is still like saying that there's two groups here, or there's this formula here that expresses how to get from the intercept to one group given the predictor. I call X the predictor in this case, and how to get to the other group given the predictor value.
So if I looked at the results and saw the diff of 0.33, and I wanted to say there's an effect size of Cohen's d of 0.33, how right would I be? Because I figure there's a more explicit way to calculate it in the Bayesian sense, but also I feel like it would be pretty close to that.
Yeah, it would be pretty close. You'd want to, let me scroll down. You'd need to, for each diff you got, multiply by the YSD
Okay, yeah,
to get the precise Cohen's d.
right, okay. But which in this case would
Yeah, I mean it's close because that's 0.99, and
Right, right.
these are going to covary pretty
okay.
decently. But you'd want to, if you wanted to express it as a credible interval on the Cohen's d value,
Right.
you'd need to take that extra step.
Cool.
So, what I'm going to show you next is to, let's see, what should I do first? This is still building towards something that we'll use more often. I told you that given this formulation of things, you still would then have to go and figure out what this, again, this diff is on the Z scale, and you'd maybe want to be reporting things back on the actual original scale. Before I get to showing you that, though, I want to show you the next step, which is to not bother having this separate intercept as a parameter and just be passing in, instead of a single vector for x, we're going to pass in a matrix for x, where one column is the intercept. And the rest of the columns are any predictors. Here we only have one predictor, group but in later scenarios, we're going to have multiple predictors. So I'll create that as a new model.
So are you saying you wouldn't scale it now?
We'll still be scaling it.
Okay.
Yep. So I'm going to copy, call this 04. So again, I'm going to say instead of a vector coming in, X is now going to be a matrix. And if it's a matrix, I need to say how many rows there are and how many columns there are. Just to make this so it's generalizing, instead of n, I'll call this ny. And so this is ny, and this is ny. And similarly, to indicate the number of columns in X, I'm going to call this, I'm going to create something called nx. So now we've got a vector of length ny coming in, and a matrix of length of number of rows ny and number of columns nx. Since we are going to construct this matrix so that it has one column that's an intercept and the other column that's the group effect, we don't need to have a separate intercept term here. We do need, instead of, I'll show you here, instead of an intercept and a diff, we need a vector of length nx, so it's going to be length 2, and I don't know, we'll call it coef for coefficients.
Can you go up a little bit?
Yeah.
So you specify that y is a vector in data, x is a vector within parameters. You don't need to like nx rather.
So this is going to be just we're gonna have something that's a matrix that has 2 columns.
Yeah.
I could have just not had that and put 2 there. I wanted to make what we're about to create flexible for later models when we have more than 2 columns in the model matrix.
Yeah.
We're going to have other predictors in the model. So that's why I said and we're going to pass it a value for nx that is equal to 2 in this case. In later cases, we may pass it that has 3 or 4. So where before we had 2 parameters as like separate things, here's an object named intercept, here's an object named diff. I've commented those out, and instead we're going to have a single vector of parameters, though it's still values, of length nx. Again, nx for this case is going to be 2. So this is a vector of 2 items.
And just conceptually, what are the 2 items, or just the provinces?
The 2 items, no, it's going to be the intercept and difference. That's going to be determined by what we do down here. So if we say the first item, you can refer to items within the vector as in R by using the square brackets. So the first item is distributed as normal. So that's the intercept. And the second one is distributed as, also normal. So we actually want the same prior on both of these things. So we don't actually need to have them both there. We can just say that vector is distributed as normal 0, 1, and that will propagate this distribution, this shape for our belief, to each element of this vector. So that's another reason why it's useful to scale, is so that you can express both your prior for the intercept and prior for the differences on the same scale and have it all as one thing.
Would you ever have coefficients that are not of that nature?
Not really. Usually we'll scale the coefficients ahead of time to make it work. So we no longer have anything called intercept, so we can't say intercept plus x times something. We also don't have anything called diff, so it's just going to be x times coef. That we have there. I'm going to save. Syntactically correct. So this is actually going to automatically take x, which has which is a matrix with 2 columns, and coef, which is a vector of 2 things. It's going to multiply the first column by the first thing in coef, and multiply the second column of x by the second thing in coef, and then add the 2 to get x, the intercept plus 1, and the intercept minus 1. Is that, have I lost you yet?
I wouldn't mind if you explained
Yeah.
it again.
Okay.
It's like a lot of code and like connections. It's really
Is this and yeah, I guess this might be what I'm missing. Is this providing us information on top of what we were seeing before, or is it just an even more like you can feed in any data set with minor modification?
Yeah, so this
Okay,
this
okay.
changed from the last one to last model, I guess model 0. Oh shoot, I've been typing in 2 samples 03.
Oh man.
I'm gonna copy this. I'm gonna press undo until it goes back to what we had before. This is what we had before, so I'll save that as 03. I'm gonna open up 04 now and whoops, no. Paste in the result there. Okay, so difference between 03 and 04 is that 03 expected a single vector as our predictor, and it handled the intercept. It just created an intercept term to add in. 04, it's not giving an intercept to the model, so it's expecting us to give a vector of 1s in this, and it will have a value in here to multiply by that 1 to get out an intercept term in this equation here.
Okay.
So it's going to have basically a 0 there, because remember the intercept, we've centered it on 0 in the data. So coef, the first element in the coef vector, is going to end up being about 0 if we've passed in, well, a matrix where there's 2 columns, one of which is all 1s, which is reflecting an intercept, and the second column is negative 1s and positive 1s to reflect our main effective group.
And why is the intercept 1 again? Not like 0.
If it's all 1s, as the it's so think of like this matrix X, the columns of being an indicator variable, and the first column is called an intercept, and the indicator variable indicates it's all 1s, and it's indicating like every entry gets an intercept.
Yeah, I understand that. Like I saw the the 2 columns,
Mm-hmm.
but then when we're thinking about the intercepts, and we've scaled the data so that they're all centered around
Mhm.
0, I don't see why the intercept is 1 rather than 0.
It's because I guess the indicator column, I'll call it that, for the intercept is going to be all 1s, indicating that when you do this multiplication out, every entry for y gets the intercept value multiplied by it. If it were all 0s, then the whatever value was in here for the intercept wouldn't be multiplied by anything.
So it kind of comes back to the regression equation, right?
Yeah.
That so because I don't remember what that is, but basically you're going to multiply stuff by the intercept.
Yeah.
And so you need to indicate what the intercept
That-
is by
yeah.
having the 1.
Yeah,
right, which you
so
then multiply by whatever the intercept is. To
yeah,
get the-
so the first entry in this thing called coef is going to contain the value for the intercept, and the columns in X in that the first column in X indicate which entries have to have that value added to them. Well, it's an intercept, so all of the entries have to have that value added to them. So, because it's
How did-
intercept plus, and then whatever else comes. So every value gets the intercept added to them.
And the intercept is represented by coef.
Well, the first entry in coef is the intercept,
Okay.
and the second entry in coef corresponds to the second column in X, whatever predictor we put there. So we will put there the group difference.
Okay.
Is that what NX is right there, or no? In
Uh,
5,
NX is going to be 2 because we're going to create a model matrix with 2 columns,
Yeah, I
one
was gonna
column
say,
that's an
maybe
intercept.
This will make more sense once we.
Okay. So I'm gonna save.
Sorry.
No, I agree. I could have planned this out a little bit better. So
I know,
if you remember, we created this model matrix, and I'll take a look at the head of it. It's got 2 columns, one that's intercept, that's all ones, one that's called group, that's -1 when it's one group, negative or +1 when it's the other group. So they're both indicator variables. This one is what you multiply by the second element in coef to get the relevant group from the intercept to the relevant group. And this is what you multiply by the first element in coef, which is the intercept. It's superfluous in a sense in that it's just always going to be 1. It's mathematically saying always go to the intercept and then go either down to get to one group or up to get to the other group.
But there are cases where it won't always be 1.
No, intercept is always 1.
I think maybe part of the confusion is that the intercept's value isn't 1. The intercept is indicated
Yes,
by.
yeah. So this is an
the symbol
indicator. Yeah.
yeah, I mean, that was kind of my question. The value is 0.
Yeah.
So,
So
isn't that messing with something somehow that we have?
no, because it's again, think of this as like an indicator. It's like what you're multiplying by the actual intercept. So, and since it's 1 all the way down, I mean, it could have been 10 all the way down or 5. That just would have scaled the intercept. 1 all the way down just means that every value gets precisely 1 intercept value added to it. If the intercept in this case is 0, it gets precisely 1 0 added to it. So it's 0.
I find this is one of the things, like if you just see the 2 by, even a 2 by 2 matrix, it helps a lot just to see how they multiply it. Do you see what I mean?
Yes.
Like
Okay.
It's tough to see sometimes how,
So-
because it's a matrix multiplication.
Yeah,
It's
yeah,
tough to
yeah.
see how
So
that's gonna
let
work.
me actually show it then.
Yeah, yeah.
For that. So, if we have maybe I'll do it sideways. Our model matrix 1, -1, 1, +1. And if we have our thing called coef, oops. So this continues on down. It actually had -1s all in a row because the groups happened to be all chunked together. Let's just imagine that I happened to interleave them. So if we have coef as equal to, let's call it, let's pretend we're not scaling. I'll say 100, 4. So the equation that we have is going to be y equals coef times mm. So what that equation is going to do is it's going to say, okay, for every row in mm, multiply the entry in the first column by the first element of coef. So for this first row, it ends up being a value of 100. So I'll say y row 1 is going to be 1 times 100 plus, and then -1 times 4. So y1 is equal to 100 minus 4 equal to 96. So that's for the first row. It works out for the first row. And then for the second row, it's still going to be 1 times 100 plus 1 times 4, which equals 104.
Why do you just add the two together?
Because that's how the idea of like matrix algebra
Yeah, okay, it's just an
works.
online
Yeah.
sound.
Because I mean, originally we had the model as being an intercept plus
Right.
x times, so it's always the intercept part is all just ones plus the difference.
Yeah, I get how it's kind of related. Like hearing you say that's how it works when you do
Mhm.
a couple multiplication. I guess it does make sense.
So the credibility in that coef value that we have, where it's 100 with, I guess, a credibility of 4, am I interpreting that correctly?
Say
Or-
again?
So when it's 100 comma 4, the 4 is the difference.
Yeah.
Okay.
So this is the intercept, and this is
Call it
the
credibility.
diff.
Your y equation there, is that like a y equals mx plus b equation?
Yep.
Where's the plus b?
That's the intercept.
Okay.
The plus b is always the intercept.
Right.
And if we make the mx part be a matrix, a vector times a matrix, and that matrix contains a column that's all ones, we don't need the plus b part.
Gotcha.
All right.
This is just like a hint at the math that we were like requesting a few classes ago. And you think we can do this? I mean,
Yeah.
This is already like.
Yeah. This is about as complicated as like it gets. Like just being able to follow that. Okay, originally we had something that was an intercept plus x times diff, to going to okay, we actually, as long as we make this a matrix with one column that's all ones, this is mathematically the same thing. That's as like, complicated as we'll need to get mathematically. I lie. There's some cool things that I'll show you down the line that are a little bit more complicated mathematically, but not much.
We didn't even like scratch the surface of what the actual sampling is doing.
Yeah, no, we haven't scratched. No. Question?
So this has in the data section. This has ny and nx. Are we going to create those?
Yep.
Okay.
Okay.
That was
So let's see. I'm going to. We've created MM, so we don't need to create that again. So here, post 4, we use 2 samples 04. We want something called ny, but it's just the same as what we had before as n, which is the number of entries in A total. And x is going to be the number of columns in the MM,
which is 2.
which is 2. And now we can just pass x is the whole MM. While that's going.
Could you go back to the stand code?
Yeah,
I mean,
well,
I'm
that's-
not going to edit it, obviously.
Mhm.
Okay.
Just while we're like waiting. So earlier you said that if the intercept is or the intercept indicator is 1 for each of those, like you didn't need to write out any kind of addition in the coefficient times.
Yeah.
But like, could you just write it out for clarity's sake?
Yeah.
Just so yeah.
So I will put it down here as a comment. Y distributed as normal something YSD. Actually, I'm not going to make it a comment till at the end because I can see it better. So this little bit up here, x times coef, is the same as x, the first column of x, times coef 1 plus the second column of x times coef 2. So if the first column of x is all 1s, that's similar to, that's kind of superfluous. You could say coef 1 plus this times coef 2, which if put in the terms we had before, that means coef 1 is the intercept, and coef 2 is the diff.
Okay, and that mathematically is the same thing as x times coef.
Yeah, the programming language knows that if you are trying to multiply a matrix by a vector, it expands it to, okay, do it element-wise and then add.
Okay, yeah, maybe we just did those as comments. Like, it's kind
Sure.
of like, expanding it just to make it a little more clear.
Are we going to be missing the divided by 2?
Yeah,
Okay.
yeah. I was gonna wait till we actually looked
Oh,
at it.
sorry.
No. Okay, so it's sampled. Double check, look at it, and we get the first coef is the, so in the printout now, this is the first time we've had something that is a vector as our parameter. So it's printed out each element of the vector with a little 1 and 2 beside it. So the first element of coef is our intercept, centered on 0. It's the same as before. The second element is that difference between the two groups that we had. And it was 0.33 before, now it's 0.17. I was going to ask you guys, why do you think that is? It's because before when we had it, we added that divide by 2 because you have to go half the difference from the intercept to get to one group and half the difference from the intercept to get to the other group. But we don't have that divide by 2 here. What would be a solution to that doesn't involve trying to say a divide by 2 in here anywhere?
Multiply it by 2 at the end or something.
Yeah, well, we could actually go, just remember that was what was going on and multiply that difference by 2 all the time. That can be annoying. The trick is to, if I look at head of MM, instead of having negative 1s and positive 1s, if I have negative 0.5s and positive 0.5s, that will be the same as multiplying this by 2. I don't have, let's see, if I just say, yeah, I could say MM second column is same as MM second column times 0.5. Now if I say head, whoops, that's going to be, MM now is going to be negative 0.5 and positive 0.5. In theory, if I run this, it'll now be back to what we actually had before.
So the first version was coef 2 was showing you the difference from the intercept,
It was showing me half the difference.
which is the distance from the intercept.
Yeah,
for each
yeah, sorry.
one. Okay.
Can you please show the code again for how you got the 0.5s and then?
Ah, okay. I'm going to give you guys a better, only now as I came here, I realized I didn't have it at hand. You can do it by hand when you have a single column by, you just say, you refer to the column in MM and overwrite it with itself times 0.5. I'm going to give you something that you can put when creating the model matrix that will automatically use 0.5 and negative 0.5. That will be more handy when you have more predictors in the model.
Is that going to be like an options
Yeah.
thing?
Yep.
Okay.
Yeah, exactly.
Yeah, I figured that. Yeah, the options function seems like there's a lot deeper you could go with it than
Yeah.
we did.
So,
And it's actually like in some ways harder to read and understand that printout when it's just in coef
yes.
form. So you just deal with that. You just know it's
Yeah, you tend to just know that the name of this is, well, actually, the thing that I was going to show you next was how to automatically, again, it's also hard because this is, again, in the Z-scale units, and if we were interested in what the actual units were of the original data set, we want to multiply that back out. So I thought I'd show you that bit next.
What would you multiply that by?
Well, if this is saying the difference is 0.33 Zs,
Okay.
what would you do to get it back to IQ values?
Oh, right, that's the difference. Okay.
You-
The standard deviation.
Yeah, you'd need to since you divided by the standard deviation to get to the Z-score scale, you multiply the sample standard deviation to get back to the.
I was just forgetting which was
yeah.
the difference and which was the mean. So.
Yeah. So I'm not going to create a new model. I'm just going to modify this 04 one. But what I'm going to do is instead of having to scale the data out here, run it on the Z scale with sort of priors that are nice default for Z scales, and then have to rescale it back in R when I get the results out. There's actually two sections that I haven't told you about. There's the data parameters model section, but you can actually define something called transformed data. So in transformed data, you need to define variables. So I'll define a new thing, vector, that's a vector, and I'll call it y scaled. But here, I can actually say y scaled is equal to y minus mean y. I'll put parentheses around it, divided by SDY. And that's what we were just doing using the scale function outside. But critically, by not passing it the scaled version of y, but scaling internal to the stan, it means that we actually still have y kicking around, and we know what SD of y is, and we know what the mean of y is. So we'd express the model not in terms of y being normally distributed, but y scaled. Because again, before we were passing in the scaled version of y as what y was. Now we're actually passing in, we're going to pass in the unscaled version of y as the value for y, and compute this new thing called y scaled. And so it's that y scaled that allows us to, if we have the model as y scaled on the left side of the tilde, that means that we can have these nice default priors. But afterwards, we can have a final section here, generated quantities. So we can say coef unscaled. So I guess I had vector nx coef. So the first element in coef is the intercept. What did we need to do to the intercept to get back to the raw value?
Multiplied by the standard deviation.
Yep, we multiply by the SD of y, the original standard deviation,
add that.
and then also add back the mean. It does matter.
It does.
Because up here we subtracted the mean first and then divided by the standard deviation. So you need to multiply by the standard deviation first and then add back in the mean. And for the second one, with the difference one, we have to multiply by the standard deviation of y because the difference is on the scale of z's in the coef, but we don't add back in the mean because the mean only affects the intercept where it is, and all the other ones are scaling coefficients, so we just need to rescale them.
So on the right side of those equations, normally when we see,
Oh.
okay, yeah.
Were you seeing that and
Yeah.
thinking, yeah. Now,
So that's specifying which one of the vector coefficient. is
Yeah.
it.
Now we happen to have a scenario where nx is going to be 2 with this data set that we're dealing with. But that, for other data sets, this model might have more predictors. In fact, I'm going to add one in just a moment. So to handle the case where this is maybe there's even like a third coefficient or a fourth coefficient that we need to rescale, instead of having this on its own line all by itself, I'm actually going to add 4 I in 2 to nx. This is a for loop. I haven't shown you guys for loops in R at all because we haven't needed them. They're really foundational to computer science in general, though, so I don't feel too bad forcing you to see one. We just haven't needed one so far. So the for loop, I have, in the same way that like you define a function and what happens inside the function with the squiggly brackets, I'm going to take this and put it inside the squiggly brackets. So if nx is 2, it's going to say for each item in the list of integers from 2 to 2, so it's just 2. It's going to temporarily assign the value of 2 to the object called I. So if I put I in there, it will then just say, okay, the ith item in coef unscaled is equal to the ith item in coef times the standard deviation of y. So it's just going to be the second item in coef unscaled is equal to the second item in coef times the standard deviation of y. But if nx is anything greater than 2, it's going to go through and multiply each one out. So the second item in coef unscaled is going to be equal to the second item in coef, and the third item in coef unscaled is equal to the third item in coef, and it's going to keep doing that until it reaches the number of items in coef.
Okay, so each, so for the first one, it's always going to be the indicator for the intercept.
Yeah.
So that's why you don't have any kind of, like that's a given.
Yeah.
For us. So for I in 2, wait, but the 2 is referring to column
Yeah.
2?
So what this little bit, so with for loops you always have a named sort of
That's arbitrary.
variable that is going to be assigned something, and that some value is always on the right-hand side of this in, and 2 colon something is saying the integers from 2 to whatever nx is. Here nx happens to be 2, so the integers from the number 2 to the number 2. So it's just one number, so I gets
Okay.
only...
And that's assuming that for all of them the conversion process is just dividing by the standard deviation.
Yep, and that's what happens when we create y-scaled, all the predictors, then their scale is on the y. Yeah, they get unscaled by multiplying by that standard deviation. So I'm going to save. Question?
Excuse my poor statistics. Use you say predictors. You mean that's the groups of BC versus?
Yeah, yeah.
X? Okay.
Yep, anything on the right-hand side here. Anything that's in this X that we're going to pass it in. So having made that change to 2 samples 04, we now no longer need to actually scale the IQ as it goes in to Stan. Stan's automatically going to scale it.
When does could you go back to the Stan file? When does NY get used, or how?
It's just counting the number of entries in y. So we needed ny to initialize this vector of the number of entries in y, the total number of IQ scores that we've measured,
Which is 200.
100 per group.
Where does that get used ultimately?
Only in creating y as, like, initializing y as a vector. We need to know how long it's going to be to initialize it. Ditto to initialize x. And I guess here we use it to initialize this thing called y scale, which is just going to be the same length as y.
Okay, so the NY is just telling that that's how long the vector is.
Yeah.
But it's not really that the actual number 200 is not used at
No.
any point. Okay,
No.
That's what I was thrown off by. Okay.
So having recompiled the model with these additions and rerun the model, this time not scaling the data ahead of time, we can look at the results. And now we get coef 1 and 2, and they're the same as before, but we also get coef unscaled 1 and 2. So there's our 107, and there's our 4-ish. So it's automatically gone and gotten out the unscaled version of those two coefficients. We could ask it to actually unscale the noise parameter, how much variability there is in each group, if we want.
Yeah, I was gonna say.
If we're actually interested in having that as part of our output.
Okay.
I'll ask you, how would we do that?
Multiplied by the standard deviation.
Okay, so what precisely would I do in my code here? Let me make it bigger.
Not the guy for that.
So you need something in transformed data, right? Or it's already there?
It's already there as a scaled.
So y scaled's already there.
Okay.
We know that this thing called ysd
Yes.
is, since it's on the right-hand side of a function of y scaled, ysd is being expressed on the scale of z scores. So in theory, in the same way that we had coef as something that was on the z scores and we wanted something new that was on the scale of the original data, we need to do something.
You need it unscaled. So would you put it in the generated quantities?
Okay, what am I going to put down here?
So you'd put ysd underscore unscaled.
Aha, okay. So real ysd underscore unscaled. There. And one thing that I haven't needed to mention yet is that it's actually, I think, going to change in the next version of Stan. You have to put, here I'm defining two things, and then I'm going to express what they should be computationally. You have to put the definitions before the computations, so I can't talk about ysd unscaled equals blah, blah, blah. If I put that and this were actually a meaningful computation, it would still give me an error because it will see a definition, computation, definition. It wants to see all the definitions in a row and the computation next. Next version of Stan, I'm pretty sure they're going to make it so that you can define and compute in the same sort of line. But for now, you have to define all your things and then do the computations. So it's a little annoying. So what do we need to do? What should y underscore unscaled be?
YSD times SDY.
Yeah. Hit save. Rerun. Make this big.
This is all assuming that the two groups have the same standard deviation,
Yep, so this is
which they
back to a somewhat restrictive model that is really the only models you guys are familiar with so far, assuming homogeneity variance. We won't have time today to illustrate how to relax that assumption, but I'll show you next time.
All our scaling is that we're using the same scaling, like based on common-
Yeah, well, we're using a scaling. We're scaling by the overall standard deviation, regardless of what group people are in.
Right.
So it's the overall noise in the.
It varies if there's an effect, and these are different samples.
Yeah. If you have a scenario where there is truly no effect, no difference between the means of the samples, then the noise you're scaling by is truly the value of the noise that's within each group. But if you actually do have a large effect, that is going to inflate the noise we're using to scale, but that doesn't have super detrimental consequences for what we're doing. So having sampled, we now have YSD unscaled. So this is the estimate for the standard deviation within each group. Again, assuming the model expresses an assumption that each group has the same standard deviation. Our plot of the histogram of the samples seems to indicate that actually that doesn't hold. Next week, we're going to show how you would actually detect that scenario and what you would do to amend the model to be more flexible to.
In this, we're doing it because as we showed before, the standard deviations in the two groups they're like super close, right?
They're actually not super
Oh,
close. If you
really?
remember, they're like if you look at the histogram.
Yeah, maybe I'm remembering.
Uh,
the wrong
I'll just
stuff.
go up to the top and do this. I intentionally made them so it
Oh,
violated
yeah,
that
right,
assumption.
right.
Like you can
Okay.
clearly see that
That's
one
right,
group is.
right. I'm thinking of. I think I'm thinking about the.
I mean, I made that assumption here because, first of all, that's the assumption of all the tools you've ever been exposed to thus far. All the regression tools you've used have assumed homogeneity variance. It's also just when building up to this final sort of model, it was easier for me to talk to you guys about things where the only effects the predictors have are on the shift of the distribution, because that's what you're familiar with. But you might start imagining what you would do if you wanted to say, okay, and there's also effects on the standard deviation. Really, what all you're going to have is another vector called like cof2, and you'd say instead of YSD here, you'd have x times cof2 here. It's going to be a little bit more complicated than that because we have to make sure that that always yields a positive value because the standard deviation can't be negative, but that's relatively straightforward to achieve.
I have a question about the scaling. So I understand that the reason that we did that is that if we wanted to be unconfident about our priors, or if we don't have any prior knowledge,
Yeah,
we scaled it
if you don't
down,
have a
right?
lot of prior knowledge,
Yeah.
converting your data to Z-scores and then using these priors
Yeah.
will reflect relatively weakly informed priors.
So, okay.
At least in our domain, where like you kind of expect the signal to noise ratio in a lot of what we do to be really low. That is, like most effects are only like 0.3, a Cohen's d of like 0.3, so 30%. The difference you expect between two groups would be about 30% the size of the amount of variability you observe within a group. So
The standardization also means there's a larger variety of data sets you could use this code on.
yes, yeah, it means that like this code will actually be generally applicable to all
It could
most
work on,
of your
like,
data
test
analysis.
scores in addition to IQ, where
Yeah.
when we were using the 100, that would pretty much only work for if we expected it.
Yeah.
However, when we previously ported it in based on the means in the data, I mean, I feel like we had this at one point where we didn't scale it, but we had like our model was based on data, and in theory that shouldn't that work just as well? Like, because the code is just looking at the data set and pulling out like the data means. And
Yeah.
whatnot.
Yeah, we could have actually hard coded in instead of scaling things, we could have hard coded in the values we were expecting.
Okay.
But this makes it a little bit more flexible, and you don't have to think about it.
So, sorry, just to clarify, the reason this works is that we have the assumption that there's a Gaussian distribution in the population.
Yeah, that's what this bit is about. Is it's saying the population is Gaussian distributed.
Yeah. And then
Within
we
each
have-
group, that each group has its own mean, but there's Gaussian error around that mean.
And then the Z score is like it's like neutral, basically.
Yes.
And the co-F we have as normal just because we looked at the data and it looked like a relatively Gaussian distribution.
That's why we're using this as normal. The data seem to be normally distributed around each individual mean. This is reflecting the shape of how we like our belief tails off on either side.
Oh, right. Okay, I'm sorry. Yep.
Yep.
I forgot that was, yep.
Wait, that's new since number 4, right?
But it's still reflecting that. So remember, we had before number 3 the intercept as being normal, peaked at 0, tapering off on either side. The diff as normal, peaked at 0, differing off on either side.
Yeah.
This coef thing just has the intercept and diff in just one thing. And it happens that the Stan language, if you just say a vector on the left-hand side, it propagates whatever you have on the right-hand side to each element in the vector. So it's the exact same. The first element in coef is normal, second element in coef is normal.
And before number 3, we had the 2 different sample like means.
So you said, so for number 2,
Oh, we still were doing it by intercept.
let's see, and what did we have? Number 1 was just the 2 different means. And again, we still had it as the mean as being centered somewhere, but this was reflecting the shape of our belief. Yeah. I guess the last little thing that I want to just show you is that now that we have this thing, this 2samples04.stan, oh, you know what? I think I saved it since the last time, and I'll show you this next time.
An alarm just telling you you saved it.
All right.
It's a very compelling alarm.
Yeah.
It really is.